So far, every circuit that has been presented has been a circuit that has DC electricity, or a direct current. For example, if we make a circuit diagram that represents a battery of some ideal voltage connected to a light bulb with a particular resistance, such as this example here, like a 1.5 volt battery, and this is maybe a single mini light, maybe one that was taken off a string of holiday light bulbs. So we know about the positive and the negative terminal of the battery. We connect one wire here, we connect the other wire here, and so there's the circuit diagram for it. Now, let's cut just one segment of this wire and blow it up. Actually, let's blow it up even more than that. Okay, well, this end over here is near the negative terminal, and this end of the wire segment over here is closer to the positive terminal. So low potential, high potential across the ends of the wire. What does that do? That creates an electric field inside of the wire that points in this direction. Now, the metal wire has free electrons in it. Let's draw some of those in. Let's say all these dots represent electrons that aren't associated with any particular atom. Well, they don't accelerate in the direction of the electric field. They accelerate opposite the direction of the field. And I know this is mainly review from the first couple of lessons from this unit, but I just want to remind you about DC so that we can talk about alternating current in the right context. Okay, so these electrons then start to accelerate to the right. Of course, they undergo collisions with other molecules. So when that happens, they convert their kinetic energy into thermal energy. The wire heats up a little bit. It mostly does that in the filament, where there's a greater number of these impurities in a smaller cross-sectional area, so less of a free path for the electrons to get through. In any case, the net effect is that the electrons have a drift speed to the right. Of course, when we talk about current, we refer to conventional current, so having electrons drift to the right is the same thing as having conventional current flow to the left. But all of this is a result of this steady electric field, which produces a steady drift current and a steady value of conventional current. If we were to graph the electric potential on the y-axis versus time, and we can graph the potential at the positive terminal of the battery, and we can graph the electric potential at the negative terminal of the battery. Now let's just put in a symbol here, and for reference, say the electric potential at the negative terminal is 0. Okay, so let's graph that in. Okay, so that line represents the electric potential at the negative terminal. It just always stays 0 as time passes by. Now the electric potential at the positive terminal, that's also just a horizontal line. In the case of a 1.5 volt battery, then okay, that's 1.5 volts. So at any moment in time, the difference in electric potential between the positive and negative terminals is 1.5 volts. So if the voltage is steady and in one direction, then the electric field is constant and in one direction, and the current flows in one direction as the electrons drift in one direction. Direct current, DC. All right, now what about AC then? Well, the outlets in our home provide AC electricity. If you take a close look, you should notice that the slot for the plug on the right side is just a little bit smaller, and then the one on the left side is a little bit longer. So this one has a electric potential that's pretty much always the same value as ground. So that, yeah, if you were to, oh gosh, accidentally put a piece of metal into an outlet, you'd be all right as long as you put it into the slot on the left. If you put it in the one on the right, we refer to that as the hot, and it's the one that has the large potential. So it's kind of like a battery has a zero electric potential, and then the positive terminal is the high potential. Although with AC, this isn't always high potential. This is a oscillating electric potential. And that really comes down to the way electricity is generated at the power plant. Anyway, if we take one wire, connect it to a light bulb, and the other one connect here, we have a complete circuit. Now the way we diagram this, there's the symbol for the light bulb, but we don't put in the symbol for a battery. That's the symbol for DC. Oops. If we were to diagram this circuit, we'd put something like this, all right? That represents an AC source. So again, we can cut out a segment of this wire and zoom in on it. Let's really zoom in like we did last time. Actually, let me skip forward to the graph of electric potential versus time. So first of all, let me graph the electric potential from this side of the outlet. Okay, well, that just stays at 0. Let's graph the electric potential for this side of the outlet. Okay, here's where things get interesting. That graph would look like this. See what I mean? It's oscillating. Sometimes it's positive, sometimes it's negative. And at most, it's 170 volts or negative 170 volts. So we'll call this V neutral, and we'll call this V hot. So there are moments in time where there's no potential difference at all. And then over this interval of time, the electric circuit is going to drive the electrons to drift in one direction, and then over this interval of time, the electrons reverse course and drift in the opposite direction. That's because the electric field that's produced for a moment in time points this way. Actually, it should draw that again. It starts out, well, let's move our time equals 0 to here, right? Let's move our origin in time here. So then initially there's no electric field in the wire at all because there's no potential difference. And then the potential difference gets greater and greater and greater and greater. So the electric field is growing, 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 and then at some point it reaches its greatest value. Okay, and then it starts to recede, and the electric field shrinks in magnitude, and eventually we get to this moment in time, and once again the electric field is equal to 0, and then the electric field starts to reverse direction, and it grows and grows and grows. Now it's pointing this way, getting greater and greater until we reach this moment in time, and it's at its greatest value, pointing in the other direction. So if we have an electric field that keeps changing direction inside the wire, then all these free electrons don't just steadily drift in one direction, they vibrate back and forth to the right and to the left at the same frequency with which this electric potential from the hot side of the outlet is oscillating. Now, where are the electrons doing that? Well, they're doing that here in this part of the wire, and here, and most importantly, they're doing it inside the filament. So whether electrons drift in one direction or they vibrate back and forth, either way, they're still undergoing collisions with the other molecules, the other impurities in that wire, and converting their energy of motion into thermal energy. In the case of an incandescent bulb, that thermal energy is great enough that it produces radiation in the visible part of the spectrum. So you may be familiar with these AC household outlets providing 120 volts. Yeah, that's a value that's pretty well known for the voltage from an outlet, but that doesn't really agree with my graph. Here I'm referencing 170 volts. Well, the idea here is what's the average difference in electric potential between the neutral and the hot? Yeah, sometimes the difference is in magnitude 170 volts, but sometimes the difference is 0 volts, right? In fact, over time, the average electric potential from the hot, it averages to 0. It spends as much time positive as it does negative, and positive and negative. So a better way to do this would be to graph the voltage squared, and then it'll turn these negatives into positives, right? Well, what's 170 squared? Whatever. Don't know that off the top of my head. Then we can figure out what's the average value to this graph. Well, it's not just straight down the middle because, just because of the curvature of each of these humps, right? So there's a couple ways that we calculate this average value. Actually, since we've squared this, one way to do is find the average value, and then whatever that average value is, take the square root of it. So it sort of undoes the squaring that we did to make all these negatives into positives. There's a name for that way of calculating an average value. It's called the RMS value, which stands for the root mean squared, right? So the root, meaning we're taking the square root, mean, as in a way of saying the average, and the mean value of something that was already squared. So the root of the mean value of something that's already been squared, the root mean squared value. And it turns out the root mean squared value, when something's oscillating between negative 170 and positive 170, is exactly what you guessed. It would be 120 volts. Now there's another way of averaging called the RAV value, which stands for rectified average value. That's not used as often. So when we study alternating current in more detail in a future chapter, we'll stick to RMS values. Anyway, for now, we're going to get into some examples of household electricity, and forgive me if I draw a circuit like this and say, here's a light bulb powered off household electricity, and there's 120 volts, and there's my resistance. What I'm doing is treating the outlet as acting the same as a source of DC with the root mean squared value of 120 volts. If I'm really paying attention, I guess I'll be careful and draw in the correct symbol for a source of potential difference that drives an alternating current. And in any case, Ohm's law then still follows, okay? Like equations for power. Power is current squared times resistance. As long as this is the root mean squared value for the current, then this is the average power provided to the appliance. So let's go into the remainder of this unit of study with some ability to distinguish between AC and DC. Thanks for watching.